Hey guys, page 23 in your packet. All right, so these are the last set of rules that we're responsible for. These are going to be inverse, trig, and so we learned this last semester. So we talked about how arcsine, arctangent, arcsecant are really the only ones we have to worry about first semester because these are the only variations, and then the ones across from it are just the negative versions of, right? Because arccosine is the same thing as arcsine, arcotangent is the same thing as arctangent, arcsecant, cosecant are the same. They're just one has negative, the other doesn't. And we talked about how the way that we remember these rules was we knew that all the numerator are the same. They all have u prime. All the denominators are the same in the sense that they all have 1 and u squared. So we said, hey, let's start with the easiest one. 1 plus u squared is arctangent. Arcsecant is the messiest one. It's got the absolute value, the square roots, but the u's are next to each other, so I know to put the u squared minus 1. And if I can figure this order, then my arcsine, I can make that slight adjustment and put the 1 first and the u and then the u squared. So antiderivative is very much like starting on this side and working our way to the left. So if you look, there's some similarity here. I know the a squared is a little bit different, but essentially something that's in antiderivative of this side will bring us back to arcsine. We got to take care of that a that we didn't have to deal with derivative, but you can see the connection, right? The a squared plus u squared looks like that 1 plus u squared turns into arctangent. Antiderivative with the absolute value and the square root will turn itself into arcsecant. All right, so we'll be working with these rules here. Okay. So let's start with example 1. So we see example 1 here, based off of what you see in front of you, which, okay, let me talk about the a and the u here. The a is going to be the constant, okay? So if there's a constant in the problem, that's going to be your a, and your u value is going to have the variable in it. Okay? So a is the constant, and the u is the variable. So for this rule here, it says the constant is the one that's positive, and the variable is the negative one. Okay. For the arctangent, both the a and u are positive, and for the arcsecant one, the variable is going to be the one that's positive, and the constant is going to be the one that's negative. So if you look at example 1, which is the best fit between these 3 rules? Third one, right? I have the square roots, I have the variable that's positive, I have the constant that's negative. Okay. So if I'm targeting arcsecant, the first thing you want to do is you want to rewrite this problem. Okay. So let's rewrite this problem. We're going to force a set of parentheses inside the radical. Now, if you can write it this way, then you're not going to make a mistake in terms of what your a and your u value is. So You're always going to do parentheses squared and parentheses squared. So we're going to in for the first parentheses and not change the overall value. Just x, right? So it's the same thing here. I just force that parentheses around the x. What can I put in here to make it same thing as 9? 3. So that's important. If you can do this, then you'll be able to pick out the correct u and the a value. Okay? We don't want to use x squared and 9. We want to use x and 3. Okay? So our u value is x, and our a value is 3. Okay? We're still going to go through du dx. We're still going to get it to look exactly like this rule before we apply it. Still going through u substitution here. I'm going to push the 5 out in front. That's just the coefficient. dx gets replaced with du. X is my u value. It's a perfect fit. And the u squared minus a squared. Sorry, I don't have the du there. I got a perfect fit with my rule. So now I'm just going to jump into my rule. 5 times 5 first, and then the 1 over a. What's my a value? 3. So I'll put the 5 and 3 together. R secant, absolute value of u, absolute value of x, over a plus c. Okay. Example 2. Integral of 1 over 4 plus x minus 1 squared. Which one does this fit best with? Second one, right? There's no square roots, right? But if we want to target our trig integral rule, we always want to see 2 sets of parentheses in the denominator with the squared outside of them. Okay, and if we're doing this so that we're picking out the correct a and the u value, when we're not making a mistake, accidentally taking the wrong one. Okay, so how can I fit this into the denominator in this form? What can I put inside here? 2, because 2 squared is the same thing as 4. I'm not changing my overall value. I'm just rewriting it. And this is not going to change, right? Still x minus 1. Okay. My a value is, yeah. Now, sometimes the problem may not present themselves with the a first and the u second, but you can always tell which one is the a and which one is u because the a is the constant and the u has a variable in it. All right, so even if these were flip-flop, you'll still be able to pick out the correct a and u value. Okay, du dx equals 1. Dx equals du. I'm putting it back in the form just to convince myself that I have a perfect match with the rule that I want to use. No leftover coefficient to keep track of, so I can jump into my rule. I'm starting off with 1 over a first. Place a with 2. U over a. So that's x minus 1 over 2. Let's see. Questions there? Okay, look at number 3 here. Which rule is best fit for this one? The arc sine, right? Because I have my constant. I got a square root, first of all. But my constant is positive and my variable is negative. So that's best fit with this first one, right? A squared minus u squared. Okay. So first thing you do is rewrite that denominator, force a parentheses squared, so that you're not accidentally picking out the incorrect u and a value. So we got to figure out, I want to create something that's equivalent to 7, but I have to put it in this form. What can I put inside here where if I square it, I end up with 7? Root 7, yeah. Right, isn't root 7 squared the same thing as 7? This will help me pick out the correct a value. Okay, what can I put inside the second parentheses where if I square this expression, I get 16x squared for x. So we do have to do some adjustment here. Otherwise, if we just pick 7 and 16x squared, we're not going to get to the correct a and u value. Everybody comfortable with that? That we're adjusting this so that we're making it easier on ourselves to pick out our a and u value. Okay, a is my constant, u has the variable in it. And you're just looking at what's inside the parentheses. Okay, du dx. Okay, I'm going to get everything in terms of a and u just to convince myself that I have a rule that matches with what I want to use. Okay, but I got to keep track of what? That 4, right? Push that 4 out in front. So now I'm jumping to my arc sine rule. Arc sine is the only one without the 1 over a in front. Okay, just the arctangent arcsecant has that additional piece. Arc sine doesn't. Okay, 1/4 comes first. Arc sine u over a. So there's my u, there's my a. There's no need to rationalize the denominator. You can leave that root 7 below and be fine. Okay, so if we think about this in general, like how do we know by looking at the problem that is not an expansion, that is not a u substitution problem? Okay, and here's the easy way for you to tell. Okay, because sometimes you're looking at this saying, okay, if I didn't know that this was our trig, I would probably go down a different path, right? It's because I've been telling you that's going to be matching up with one of these rules. That's why you're following along. But if this was just given to you at random, how do you know whether it's going to be our trig rule? So here is a way to tell. You look at that degree difference between the highest degree in the numerator and denominator. If the degree in the denominator is 2 or higher, you see how that degree is 0, that degree is 2. That's an indication that it's not just going to be a u substitution. It's going to be something involving our trig. Right, we know that U substitution is good if the degree in the bottom is higher by 1 than the top, because we know that the derivative is going to go down 1 degree, is going to pair up nicely. But if your gap is 2 or more, then that's an indication that it's probably going to be an R trig. So if you look at here, degree 2, degree 0, right? Degree 2, degree 0. I know the square root takes away that x squared, but you're just looking at what's inside the expression. Don't worry about the overall. If you just look at that x squared and that 0, that's an indication that our trig is going to be the better fit if the denominator is higher than the top by 2 degrees or more. Okay, so the other complexity is going to come when the problems are not set up nicely with A and U. And we have to pick out the A and U ourselves. And we have to go through something called completing the square to force a situation where we can get A and the U nicely identified. Okay, but if you look at example 4, you can tell that this could be a good fit for our trig because degree 2, degree 0, right? That gap indicates that our trig is probably going to be the way to go. But that denominator is not set up nicely where we have a parentheses squared and a parentheses squared. Okay. So to force this trinomial into a binomial or a parentheses squared, we're going to go through this completing the square steps to get that denominator in a better form for us to identify the A and U value. Okay, so I'm going to off to the side here. I'm just going to focus on the x squared minus 6x plus 13. I'm going to complete the square just for this expression. Okay, so the way you do it is make sure it's in order. Your degree is highest degree, degree 1, and then the constant. Okay, then you're going to add spaces between the second and third term and after the last term. But you're going to make these spaces different signs. So the big picture is that we want these two to be the same values, but we want to add and subtract it so that we're not changing the overall value of this expression. Okay? Because whatever I add, I can just subtract away. I'm still maintaining the same value. I'm just able to create a different version of this expression. Okay, everybody good with what I did here? So what to fill in those spaces? It's going to be b over 2 squared. Your b value is going to be what's in front of your x. Don't worry about the negative and positive. It's always going to be positive because it's always squared. So b over 2 squared is 6 over 2 squared. 3 squared is 9. So plus 9 minus 9. Now, the nice thing is that this is going to factor out to be something binomial squared. It multiplies to be 9, adds up to be negative 6. It's going to be negative 3 and negative 3, right? So now I'm going to clean this up a little bit more. I'm going to say x minus 3 squared plus 4. So we're getting closer towards our A and U value, right? We see clearly 2 sets of parentheses, or we can force that parentheses with that 4 as well. So here is my starting point to begin my process. What can I replace 4 with so that it can be parentheses squared? 2. Again, we see the same degree relationship here, degree 2, degree 0. There's a gap of 2 or more. Which our trig is going to be the best fit? Second one, right? There's no square root, and they're both the same signs. Again, their A and U value may be maybe out of order, but you know which one of your U and your A value is, right? Your A is the constant, your U value has the variable in it. Okay, I'm making my substitutions just to convince myself that I'm able to get a perfect match with the rule that I want to use. Now I'm ready. 1 over A, our tangent, U over A. Let's see. Okay, let's do another practice with this step here, but I'm gonna make this problem a little bit easier. I'm gonna take away that 2x minus. I'm just gonna make it 5. We're not gonna have to do something as complicated as that. So 5 over x squared plus 2x plus 2. Okay, how do you know by looking at this that this is going to be an arc-trig problem? Yeah, degree 2, degree 0. There's a gap of 2 or more, and the higher degrees in the denominator, we know that gap is going to be a good fit for my arc-trig. Okay, let's focus on that denominator because it's not in this nice and clean form of parentheses squared plus parentheses squared. Completing the square will help us get there. Okay, what's my b value? 2. 2 over 2 is 1 squared is 1. So 1 here, 1 here. Okay, we're going to force this to factor. 1 multiplies to be 1, adds up to be 2. 1 and 1, you're always going to get the same numbers so that it will force it to factor nicely. Here's my updated problem. I forced the parentheses to be parentheses squared plus 1. This is the only time that you're going to get that to be the same thing, right? So 1 is the same thing as 1 squared. Okay, which rule is the best fit for this? Arctangent, right? No parentheses, sorry, no radical. Okay, any questions here? Go to the very last page. I have this is all filled out, but the previous page is the blank one. And I just wanted to kind of quickly give a big overview in terms of, if you're looking at an integral problem, right, how do you know whether something is to expand versus use substitution versus synthetic or long division or trig? It all kind of feels the same, right? So I want to just point out some key things to look for. So right, the key thing to look for is if you see a bunch of fractions, right, how do you know which one it is? This could be anything. Start off with your denominator. Okay, if there's only one term in the denominator, it doesn't matter what the degree is, you can always split up, right? If only one term in the denominator, you can always split up. It doesn't matter whether the degree is higher in the denominator or the numerator. We don't care about the comparison. We just split up and handle them independently. Right. Now, as soon as there's more than one term in the denominator, you know that expansion is out. You got to look at some other options. Okay. So in this case, if you look at both under the on that row 2 here, notice that my degree is higher than my numerator, but it's only off by 1, right? Don't worry about the radical. Just look at the x cubed, x squared, x to the first power. That's going to be a good fit for u substitution in the denominator, right? Because you know that the derivative is going to clean up nicely and match up with the top. Okay, so that's a good indication that there's going to be a u substitution with that denominator. Now the third row here is where there's more than one term in the denominator, expansion is out, but you see the degree is either the same or higher up top. If it's the same or higher above, you can go through long division, but synthetic is only reserved for if your denominator is x to the first power. Okay, if it's anything higher than 1, you got to go through long division. Long division, synthetic division, it doesn't solve the problem. It just presents an easier version of the problem for you to solve. And finally, the scenario where there's multiple terms in the denominator, but your degree in the denominator is higher, but it's more than 2, or 2 or more. So degree 2, degree 0, that's a good fit for our trig. Degree 4, degree 1, that's a good fit for our trig. So all these similarities, I wanted to put them all next to each other so that you guys I can kind of pick out what to look for, especially if you're looking at a problem and you have no idea, where to start, right? So hopefully this will kind of help you at least know where, what to look for so you know how to get started with the problem. So why don't we do these 2 problems on page 27, right, just to get more art trig practice. Go ahead and try these 2 problems. If you feel like there's not enough room here, go to the previous page, page 26. There's a gap here. You can use the space there, but go ahead and try the first problem. I'll go through it, and then the second one as well. And you know both are trig because that degree difference is helping you see that relationship. So the first one requires completing the square, but the second one, it doesn't. You can just jump directly into creating your parentheses for the second one. But the first one, we do need to complete the square.
Oh, this is so this those people 12 instead of 15. Yeah.
Sorry, guys. That middle number is not a good fit for this problem. Let me, yeah, I messed up on the key here. So do this one instead. This is better. Sorry. That 8 messed things up. It didn't quite work out the way I wanted to. Okay, we're gonna finish off with practicing a bit more with solving differential equations. So go to page 21. Practice more with separating variables, taking antiderivative both sides. So page 21, let's see if we can get through number 5 and 6. Okay, page 21, number 5. W prime equals t squared secant squared 2t cubed. Find the particular solution. Okay. What's different about this differential equation? The variables are different, right? Instead of x and y, we're seeing t and w. So we'll treat t the same way as what? X, and w the same way as y. So what do you think we can do to rewrite that w prime? dw dt. Exactly. And the more that we see it, the more comfortable we're going to get. Now, I'll take back to what I said before. Sometimes I do see some problems that aren't always in terms of t and some other variable. So if that's the case, then the top variable is your dependent. Your bottom variable is your independent. Whatever's at the bottom, that's your x. Whatever's at the top, that's your quote unquote y. Okay, so cross multiply, you want your w's on the left, everything else on the right. Okay, so what do we notice here? Left side, we're going to handle using what? Right side, we're going to use what first? Too messy, right? I gotta go through use substitution. What's my u value? Yeah. What's inside the parentheses? Okay, that's your u value. Okay, so that means you gotta go through a whole other step just to get that right side cleaned up. So we gotta take our time with this one. So I'm just holding off on the left side until I get that right side level with that left side. And then once both sides are ready, then I can take the antiderivative all at the same time for both sides. So the t squared will cancel out, but there's a 1/6 that's going to be left out in front. What's secant squared antiderivative? Tangent, yeah. I can only choose one of the square roots. Which one will it be? How do we tell? Look at the y value, right? The y value is negative, so I want the negative square root. Okay, number 6. Okay, let's separate those two terms on opposite sides of the equation. Get the dy dx to show up, cross multiply. Okay, the dy dx are lined up, those are good to go. But quite a few things out of place, one needs to be moved. Yeah, so the y has to move to the left, it's gonna end up in the denominator. What else?
X.
X and ln x is going to move to the right, that's gonna end up in the denominator on the right side. So both are gonna swap places and both are gonna end up in the denominator. We want the y's on the left, x is on the right. Okay, what rule do we use for the left side? Yeah, 1 over u to u, natural log. What about the right side? Substitution, what's my u value? Natural log of x, yeah, the derivative of natural log of x is 1 over x, the derivative is gonna handle nicely with that x left over. So left side is gonna be natural log of y. The right side, it will turn out to be a 1 over u du, so it's also natural log on the right side. After you go through your u substitution. So you got two sets of natural log rules going on here. Okay, so that plus c shows up. I want to raise both sides base e because I want to take care of that left side, but along the way, the right side will get handled as well. The left side becomes just absolute value of y. The right side I'll separate e to ln of x times e to the c. E to the c becomes one big C. E and ln will cancel out, so the natural log of x also drops down. The c will absorb both of the positive and negatives from the absolute value, so just left with y equals c natural log of x. At this point, I feel like this is the easiest equation I'm going to get. I'm going to plug in my order pair. E for x, E and for y, solve for c. Once I update my c value, I can write my particular. Natural log of B is 1, C equals E. So Y equals E natural log of X. Just taking this equation, replacing C with a numeric value. Okay, you got your homework tonight. From 5.7. And tomorrow we'll start test review and we'll do some more flow field review. All right, tomorrow get your phone.
When to go to my office. Do you just always do it? But.
It's up to you. For me, I'm trying to, this is just my preference. My preference is I would prefer to plug in my order pair. My equation is quote unquote the simplest thing.
Okay.
So, and I know that I gotta deal with that two down the road, so I just decided to just get rid of that two. We'll find that two over, and then I feel like everything's in. However, if you plug in your order pair at this point, you're gonna get different C value, but then multiply it 2 through, it's just still another the same.
Right, okay, got it. Thank you.
Wait, so why was the 8 work? It's like.
Yeah, so the problem is that, see that 4 by 16. And then they 12 different bits of double, so that's why. Because both terms are equal. And so, if it's a, if you that's plus 12 by 2. And then, and this doesn't work with this.
So there's no rule for.
There's no rule for that. I wouldn't be able to.
Yeah,
On my grade.
Serious bias. That's so smart. That's, yeah, that's true.
Why couldn't you do it like this, where you just put like E into here?
It's good.
You about, gosh, yeah, I was on the one. No, like, there's like mastermind. No, literally, he got.
Yes, if you did that, you would put the 1 back
The
here.
guy was like so cocky. He just thought he was doing something.
That I'm not leaving until he gives
He's
me
like,
his.
I will wait here all night.
Like, I have nothing to do.
And we're like, okay. So then I like pulled my car. I like, we were acting all slick. We're like, where we were like in the exit. Yeah, so we're like, so big ditch. Andrew's parked here, Emily's parked here. We were like acting like we're like, oh, bye, Andrew. Like, and I pulled my car up to the other side of the bushes. We got the guy was like so cocky.
Oh, okay.
I'm gonna wait here. And he stood in, he was in his car. He was literally in his car, like the car parked, everything. Didn't even have his water that he held. Yeah. And so he literally was like looking at his phone, and just got out of his car, ran and got into my car. And jumped on the hedge of bushes. What? Parking lot. Like,